satisfied. Therefore, the probability measure defined in this way, defined in defined in this way, defined in this way, satisfies the axioms of probability measure. Okay, so it's a probability. All right. Okay, then move on to the next topic, conditional probability. Okay, suppose we have a probability space and let's say A and B are events. So that means A and B are elements of F, and assume the probability of B is positive. It's not zero. Okay. Then conditional probability of event A given B is defined as the probability of A intersection B divided by the probability of B. So it's probability of A given B. Okay, given B. So this is the definition of the conditional probability. Okay. Uh, if you don't know the definition, you are in trouble, big trouble. So try to understand this definition. So what does this mean? Why do we divide by this probability? Okay, so probability is called probability measure. So it measures something, and that something is the size of events in some sense. Right? Of course, this size has a meaning in practical applications, such that this size is proportional to the possibility of occurrence of some events, right? So that's the probability. Now we divide this probability with this probability. So what does it mean? So this is also a measure of some size of probability, but with respect to the size of event B. Okay. So this is a kind of measuring the event size of event A with respect to the size of event B. Okay. So if we have this sample space omega, so this is the universe. So it contains everything we want to know. And here's event A and event B. And so A intersect B is this part. And we divide this part by this area. Okay, so that means this conditional probability is a relative size of this area with respect to B. Okay. Then compare this with the ordinary probability of event A. So event A. So probability of event A is, in a sense, it's a size of A, set A, with respect to omega, right? Because probability of omega is always 1. So probability of A is always less than or equal to 1. So you may say any probability is actually a conditional probability given omega. Okay, so we may actually write this probability as conditional probability A given omega. So according to this definition, this is probability of A intersection omega divided by probability of omega. Of course, according to the axiom of probability, this part is 1. So this part is 1, and this any event is necessarily a subset of omega. So this is actually equal to this probability of A divided by 1. So actually this one, same thing. So consider this ordinary probability as a abbreviation of this conditional probability given omega. So if we define the universe, then we can calculate a probability. And in this case, we kind of pretend that our universe is now restricted to B, inside B. So now pretend that our universe is inside B, then calculate the probability of A. So we do not care about this outside B. Okay, this region of A, we don't care when we calculate this conditional probability. Okay. So as such, if we calculate the conditional probability of B given B, then what's that value? Okay, according to the definition, it's B intersect B divided by probability of B. But B intersect B is of course B. So it's this. So it's 1. So it's just like this conditional probability behaves just like the probability of omega. It's 1, and this is 1. So now, so you can see that when we calculate the conditional probability given B, we are now pretending or assuming that our universe is now B rather than omega. Okay. And from the definition of conditional probability, we can derive a useful expression. So just multiply both sides by probability of B. Then we have probability of A intersection B is equal to probability of A given B times probability of B. Okay, sometimes we call this the law of multiplication of probabilities. Okay. This A intersect B, this probability is not, in general, this is not equal to probability of A times probability of B. Okay, but we need conditional probability here. Okay, but there are some cases where this is equal to this, and that case we define separately. So if probability of A intersect B happens to be equal to the product of probability A and probability B. This doesn't happen always, but in some cases it happens. This holds. Then we say A and B are independent. So independent. Independent. Okay, so this is the defining equation for independence of two events. Okay. So this is the law of multiplication. And what do you think the law of addition is? Actually, we've seen this before. So if there are two events, and if they are disjoint, then the probability of A union B is equal to probability of A plus probability of B. Okay? So if this disjointness holds, then we can add the two probabilities to have the probability of the union. Why does this hold? Because this holds from the definition of the probability measure. Remember the axiom 3? We had this condition. So this is the special case of the third condition, where there are only two sets. Now, of course, in the axiom we had infinitely many subsets like this. But in this case, consider A1 is A and A2 is B and everything else is empty. Then this is the same case, right? Because A union, B union, everything else is same as A union and B union, A union B. So this comes right from the axiom.